I took those pictures from my balcony. So it's the hostel across the way. It's where all the faculty, visiting faculty stay. It's actually very nice. And so this is from my room. So imagine we have a rooftop, okay, that has a downspout, which this one does, and they want to use the water there to irrigate a lawn. All right. So that's a relatively simple model, but they don't want to irrigate it year long. For what reason? Because they don't have to, right? They don't have to, because the irrigation would only needs to run from September through April. All right, because once May comes, there's plenty of rain. Now, in an ideal world, and I don't know if you can run your model, you would use Delhi or Roorkee data, rainfall data, to test this out. All right, and I have used some relatively simple imperial to SI. When did India stop using imperial units? The 70s, the 80s? I know you guys were alive then. I don't know if that's something you learned when they stopped. The United States obviously still uses imperial units. It's just what it is. But I've used some relatively simple conversions. 25 meters, it should be square meters, is a roughly 250 square feet, and 400 gallons is roughly 1,500 liters. Okay, so just understand that, and you have to. The model is all in imperial units. So just so you know that these are roughly the numbers that we're talking about, and we want to find out how big that tank needs to be. All right, that would go down here. The tank would go down here and be used again to irrigate this area. Everyone have those units. Now, I don't know if the model you have, you can use the Delhi rainfall. I didn't get to check that. I have lots of different rainfalls, but I don't have any for India. I don't have any for northern India. So I can run this model. But it's going to be with US rainfall. So it's not going to give you the true answer, okay? Because remember I told you, in America, or in the southeast of America, it rains reliably every month, okay? So I don't know if we have the Delhi rain. If we don't, we're going to go ahead and I'll show you how the model works, but just, you can't trust the output. The output will be incorrect. The type of output won't be, but the output will be incorrect, because so much of how well a rainwater harvesting system works is based upon the rainfall record that you have, okay? But let's go ahead, and I'm going to try to show you how it would work. All right, so I'm going to escape from here. Boom, everyone I saw writing this down. And then I'm going to go ahead and open up the rainwater harvesting model. Okay. I'm going to stop sharing that. Oh yeah, there it is, perfect. Wait, go away. Okay. So does everybody see this okay? I know it's small. Are people able to open up Rainwater Harvester on your computer? Okay. So can you see this screen, or is it too small? All right. So what we're going to do is I'm going to go ahead, I'm going to plug the numbers up. So 25 square meters is about 250 square feet, okay? And then the next question we'd ask is, what community is this located in? And the reason that's important is for tax purposes. I'll explain that in a second. All right. All right, so I'm just filling in. Oh, you know what? It's interesting. There's a delay, guys, from when I type it in to what when it registers. Okay. Thank you. You're going to probably have to help me multiple times. Okay. And what this what this is for is it tells you how much a community charges for water. Remember I mentioned how the government supplies us water. Some of you might be paying your water bills right now, all right? Most of you probably don't. All right? If you live in university subsidized housing, they're just charging you one bill. That includes the cost of water. All right? But if you take water from the government, they charge you for every liter or every 1,000 liters of water that you take. All right? Well, the same is true in America, except they charge you by the gallon, which remember is 3.78 liters. And so one of the things is if you use a rainwater tank and you're harvesting water from a roof and then supplying that water for something that you want, that means specifically you're not using city water and you're not paying for city water, okay? But you know what you are potentially paying for, and that is sewer costs. So the cities will charge you to use their water, and then they also charge you to basically flush your toilets and have that go to a treatment plant, all right? And the added benefit of being at IIT Roorkee is if you live in Roorkee, then your waste goes right through your campus. And how exciting is that? All right, so this model finds out how much everything costs in the jurisdiction because it needs that information when it's trying to estimate how much money you're saving by not buying city water, right? So if you're not buying city water, it wants to know how much money you're saving. So that's what this first batch of questions is about. All right. Now, the next thing we're going to look at is that is a sloping roof. So we're going to go ahead and use that. So next thing that happens, when rainfall comes and hits a roof, does all of that water that hits the roof find its way to a gutter? No, your gut is right. It doesn't. All right. Some fraction of raindrops literally, if it's near the edge, will bounce off a roof. Not much, but some of it. The more likely thing is that gutters will clog, right? And so we know that over the course of a long term, that some gutters will clog. You'll have gutter overflow. All right. And so this model will account for that. So gutter overflow. So that's known as a capture factor. All right. So what this says here is that 0.9, so 90% of the rain that falls onto a roof will actually find its way into a downspout for capture. That's actually a pretty reasonable number as well. All right. So then the next thing we're going to look at is the water quality. So what's the water running off? And in North Carolina, we have this pre-programmed in, all right? And so it's coming off a roof. And so therefore it's using numbers that we've collected in North Carolina for your typical pollutant concentration. And then they want to know what the water quality volume is associated with your storm. Now we calculated that yesterday. We have two numbers, 17 and 35. Which one do you guys like to use today? They're going to use 35. You're going to be aggressive. Okay, great. So 35 divided by 25 is about 1.7. Anyone want to verify that for me? 35 divided by 25 is about 1.7. Is that right? No, it's not. 1.3, 1.4, 1.4. Thank you for verifying, as I would have been wrong. All right. And so the water quality depth in this case is 1.4 inches. All right. And then I'm not going to use the passive release right now. So then this is helping us determine what the pollutant load is that we're trying to capture over the course of a long term. All right. So 1.4 inches, and then the concentrations. Now, there's a couple other questions that you can ask yourself. There are times where, let's say, you're using your harvested rainwater to flush toilets. Okay? Do you ever want your tank to go dry? Never, right? Never. And so what people will do is they'll actually take city water, and if the tank gets really close to being empty, they'll pump city water into your tank. All right? So the term for that is called backup water. It's a backup supply. All right? So it's the city water that you add to that. Now we have the ability to and that's what this window here is about. Do you want to add backup water? And the answer is no, not for irrigation. If it's dry, it's dry. We don't care. Okay? So that's that one. Then there is the optimal versus designated volume. We are going to pick a designated volume. And then passive release. You guys remember what passive release is? Passive release is the hole in the tank. You got it. I saw that. Boop. Passive release is are you going to put a hole in the tank? We will put our hole in the tank later. All right, we're going to just let the tank be hole free. All right. So I'm going to let that go. So I'm not going to click passive release, and we're going to end up picking, and we're not going to add any particular water to the system. All right. So then I said that we were going to use the water outside. How many gallons a week did I say? Or month? Was it 400? 400. 400 a month. Is that what I said? Or a week or a day? A day? 400 a week. So 400 a week divided by 7 is, what's that? 65? 70? Okay, that's pretty good. 65, 70. That counts as an A in my book. All right. If you do it in your head, that's perfect. So 67, we'll go with 65. We'll go with 70. All right. And then we're going to do, in what months are we doing that? Do you remember? What months are we irrigating? September to April. All right. So I'm putting 65 gallons a week. Do y'all see me doing this okay? 65 gallons a week, or gallons a day, rather, all right? Every day of the week. 65 gallons a day, every day of the week. And we're going to do that in January, February, March, and April, all right? Oh, that's interesting. Try that again. We're going to go with 65. I appreciate your desire to be precise. We're going to make this close enough, okay? But I appreciate your desire to be precise. One thing you'll know with stormwater people is we're sort of precise. It makes a lot of non-stormwater engineers very uncomfortable with my sort of precision. And then we irrigate again in September? Is that right? Is that what I said? Do you guys remember? I tell you what, I'll make you happier. I'm going to go with 70 on this side. And so that way we have 70 and we have 65. Put them together, it's almost 67.1, right? Seventy. Part of the reason we have differences in days is some uses people don't use them on the weekend. And then sometimes people are only allowed to use the water on like odd days. It's like Mondays, Wednesdays, and Fridays. So you guys see all this? Is this working up on that screen there? You see 70 gallons a day. Remember, 70 gallons a day is about 250 liters a day. Okay. And then when do you think we irrigate? Irrigation tends to occur in the morning, all right? So I'm going to have the irrigation occurring 6, 7, and 8 a.m. Why would you irrigate in the morning? There's a good reason for it. What's that?
Evaporation loss will be less.
That's exactly right. That's your evaporation losses are much lower. So you're not losing your water if you irrigate in the morning. All right. That's why but if you irrigate overnight, no one's there to check it. Right. So if you irrigate in the morning, you see that means people can be around. They can observe it. You're not going to try to make someone come in at 2 in the morning to make sure the irrigation system's working. Right. So irrigate in the morning, but not the early morning, overnight typically. All right. So we have just about everything done. I'm going to go ahead and save that. And then I'm going to go back to the system design. And there's one more really important piece. I had neglected it. And it's the actual rainfall. All right. I'm going to go ahead and use daily rain for a place that has roughly the same total rain as Roorkee, but the distribution is going to be different. And so now we should have everything we need to run the model. All right. So I'm going to go ahead and hit the simulate button. Let's hope it works. Okay. It's spinning. Let's see how it goes. We got something. Oh, but I made a mistake. You know what it is? I talk about let's see if you guys can tell what my mistake is. I look at the annual volume of runoff generated from my roof. It's 6,812 gallons, but I don't have any runoff captured. Why is that? Because I made an important omission. You know what it was? I forgot to say how big the tank was. So right now it thinks the tank is 0. And it is 0 because I haven't put one in. So let's see what the benefit is of actually having a tank that has a size. And so 500 liters is equivalent to about 150 gallons. So I'm going to go ahead and start with 150 gallons. That's a 500 liter tank. So it's a very similar tank. It's the same tank size, or essentially the same tank size as, wait a second, yeah, it's about that. It's a little higher, but it's about the same tank size as what we saw perched above the doorway behind the Water Resources Planning Building. Okay. So now we've got a tank size. We're going to run our model again, and let's see how well it works. Simulate, simulate, simulate. Oh, it did it. Oh, it did. It ran. Okay, great. So now I've got a 150 gallon tank, and it captured, check this out, 52% of all the water, okay, that fell on that roof was captured. All right. Which is, and then then it tells you the number of gallons actually. And then when it looked at the 35 millimeter rainstorm, it looks at the times that we had storms that were approximately that size, and it looked to see how much we captured of that storm size. And the answer is we captured 57% of the 35 millimeter storm on average. All right. Now, right off the bat, and then we used 3,508 gallons, which is pretty good over the course of that year. That's actually not a terribly bad performing system. That was a pretty good guess to start off with. But are you happy with 57%? You're not. I know you're not. And so do you want it to be higher or lower? You want it to be more. So what's one thing that we can do to try to capture more? It's the only thing we can do, right? Because the roof is staying the same. We increase the tank size. So what do you want to do? You want to try to double the tank size? Triple the tank size? You want to go big? Let's double it. So we're going to go from 150 to 300. Let's see what happens. One of the things I like about doing this type of doing this model is you start getting a feel for what's happening with your tank and what's happening with your design. So I've hit the simulation button. These results here will roll over here. And when I have my students do this assignment, what they'll do is when they start getting close, they'll start copying this and putting it into a spreadsheet. All right. So here we go. We doubled the size of the tank. All right. Instead of capturing 52% of annual runoff, we're capturing 62%. And instead of capturing 57% of the 35 millimeter event, we captured 65%. It's better. Are you satisfied? I know you. You're achievers. You wanted me to use 67.1 gallons. You're achievers. You want me to do better than that. All right, you want to double it again? We're going to go from we went from 150 to 300. Now we're going to go from 300 to 600. You guys excited to see what happens? I know I am. All right, 600. Here it goes. So remember, we had 52 and 57. We jumped up to 62 and 65. Now we made it really big, and it's 69 and 70. Are you satisfied yet? I know you're not. I'm looking at you. None of you are satisfied. All right, you want to double it again? Now, keep in mind that it's a relatively small, it's a 25 square meter roof, right? So at some point, you're going to have this monster tank that dwarfs what we, but I'll go ahead and I'll double it again. All right. So we're going to go from 600 gallons. So 600 gallons, about 22,000 liters. Okay. Pretty big tank. We'll double it one more time, and then we're going to have a little discussion. 1,200 gallons. Man, that is a lot. That is a lot of storage. All right, so we went from 57 to 62. No, 52 to 62. Now we're at 78. And we're hitting 78% of the capture volume, and our tank is really big. What's happening here? Why aren't we hitting 90? Is an important reason. Why aren't we hitting 90%? When are we irrigating? September, October, November, December, January, February, April. That's it. So guess what? If you're not emptying the tank in May, June, July, and August, you're never going to be able to get it to zero unless you build a ridiculously large tank. All right? Basically, what you'd have to do is build a tank so big that it would store the June, July, August, and May, June, July, and August water, and that's the only way you can get this to 100. And does anyone want to build a tank that's, by the way, that's already what's happening. That's why you're able to creep up, is that you're busy building a huge tank. This tank is probably about, at this point at 1,200, it's probably 3 times bigger than it needs to be. The optimal size probably was right around the first or second one, probably the second one we tried, because you're just never going to get it, right? You would have gotten a similar but more profound result if you had used Delhi rainfall, okay? Because think about the proportion of rain that's actually falling in May, June, July, in August in Delhi relative to the rest of the year? What did Delhi's rainfall, and actually it was Roorkee's rainfall, but it's the same thing. Low, 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 boom, 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 low, low, low. And so it's during that low time that we're trying to irrigate, but when it's at 240 millimeters in a month and 180 millimeters in a month, we're not irrigating. All right? And so the same effect that you're seeing right here was we can't get all the water. Well, that's because you're not dumping the water out. There's no withdrawal for that water. So what is a way to get rid of the water in the times that you're not irrigating? Is that your answer? That's the correct answer. Put that hole in there. All right. So now what we'll do is I'm going to use the design we have, which is oversized, but I'm going to use the design we have. All right. And all I'm going to do is put a hole in it. All right. Which means I'm going to use passive release. And of that 1,200 gallons, I'm going to dedicate 600 of them, all right, to detention. And I want to draw that 600 gallons out over the course of 3 days. So what's my drawdown rate going to be in gallons per hour? I want 600 gallons. How do you calculate it? 600 gallons I want to draw out over the course of 3 days. What's 600 divided by 72? 85? Say it again.
8.3 gallons per hour.
8.3 gallons per hour. Sounds good to me. 8.3. You're like, why are you using his precision? Okay, I'll just go with 8. 8 gallons an hour. And for kicks and giggles, we'll divert it to an infiltration zone. So now let's see how this performance changes. Remember, we have 78 and 78. Let's see what changes when we simulate that. See what happened? We went to 100 and 100. So what does that tell you about the tank now? Is it perfect? Not. That's right, it's not. What is it? It's too big. It's too big. Okay? And so what you would then do is make it smaller, but clearly from a stormwater perspective, adding that hole, man, that did the trick. Adding the hole did the trick. And therefore, every time we had that 35 millimeter event, there was enough space in there to capture it. Isn't that cool? All right. So this is how this model would work. As I said, if it were Delhi rainfall, it would have even been more extreme. Or Roorkee rainfall, it would be even more extreme. So the role of that little hole is extra important in your rain tanks for a place like here. All right. Now, I guess I do have a 5:30 meeting that I already pushed back from 5. If you can't use the model in your computer, then you can't use the model in your computer, and that's, I guess, the end of the story, isn't it? What I'll try to do, how many of you, if we could get it working, would be interested and you have a project you'd want to use it? Okay, that's a decent number of you. I will talk with Vinnarasi and see what we can do about trying to get that model to work. And honestly, if anyone's looking for a master's degree, maybe you could take it and make it work for India. I mean, it's open source. Well, in that I would share it with you. It's open source and I'd open it up for you. But if it's something you wanted to use here, I'm happy for you guys to use it. But you need to do some programming on it and obviously get the right rainfall that you would use. But the rainfall is not that hard to generate. You have any questions? Okay. Okay. The one last thing I want to share with you, and I know the guys can be like, "Where are you going, buddy?" I don't want to stop sharing. I'm just gonna get rid of this. All right. I'm gonna come back and I mentioned this once, but I wanted to mention it one more time. This. Um, there are times where you would harvest water. This is a lot of harvesting, right? There are times you would harvest water from rooftops that you want to then move to somewhere else. All right. And that would involve pumps. Rainwater harvesting also often has pumps involved. All right. So you capture the water here and then you locate it somewhere else for you to use it via gravity. All right. And that's what was happening, as I mentioned here in Jordan, that water is being pumped. I swear I saw some of this in Delhi. The water is being pumped onto these roof tanks that then supply water for the inhabitants of that building. Okay? So just be mindful that that is a common thing that you would have at your disposal if you wanted to harvest rainwater and then put it somewhere else. You can harvest it if you want right next to your building, and then over the course of a 24-hour window or using a solar pump, you can move that water at a very low rate to another place where the water would be a lot more useful, but it's also a lot farther away from the building. All right. So just be mindful of that when you're dealing with rainwater harvesting. You have this ability to move water from where you capture it to another location, and in doing so, you're actually creating more storage volume in the tanks next to the building for your next storm. All right, that's just the last thing I wanted to kind of drive that point home, is I think that might be useful here. All right, I have to get going. I'm glad we got to spend a little extra time today. All right. Yes. Say it again. I think it makes a lot of sense, actually, if the roof is strong enough. All right. Because the use of the water, it can be driven by head. All right, depending on what you're going to do with it, but it can be driven just by pressure head for where you're trying to use the water. All right, and so it is a very common thing that's done, uh, especially in the Middle East. I saw it in Jordan, but I've seen pictures of it elsewhere and in the Caribbean and south of the United States, the Caribbean islands. They all use that, and it seems to be very practical for them to use it. Just the thing is, your roof has to be designed to be strong enough to handle it. All right. So this is a question that you'd always want to ask your structural engineer to see if he or she thinks that, in fact, the roof is strong enough. Good question. All right, guys. I actually hate leaving you, as I've had a good day today. I'm going to try to sleep well again tonight so I can bring the energy for you tomorrow. Tomorrow we're gonna talk about permeable pavement tomorrow. I think permeable pavement has a large application here on campus. All right. Um, so we're gonna talk permeable pavement tomorrow. Which is not what we had planned. I had planned to do swales tomorrow. So I actually I have to adjust some stuff. I have to work on some presentations for y'all tonight. So we're good shape tomorrow. But tomorrow will be permeable pavement day, and we'll create a simple Excel spreadsheet to help figure out how well your permeable pavement will work for a specific storm you're trying to capture. Sound like a plan? Okay, great. You guys have a great evening. It's good seeing everybody. Have a great evening. I'll see you tomorrow at 10 o'clock. And thank you for all my hats.